All right. Hello, everyone. Welcome back to a summer in linear algebra. Today, we will be talking about the dot product. So the dot product is a way of multiplying two vectors together. We mentioned that in the last video. We talked about a different form of multiplication called scalar multiplication, where you take a number and multiply it times a vector. Okay. This is going to be different. This is a notion of what it means to multiply two vectors together. And what we'll see is that we can use this strange notion of multiplying two vectors together to define different geometric properties of vectors. For example, length of a vector, distance between two vectors, or angle, that kind of thing. Let's dive in. So I'm going to start with a totally unmotivated definition. We're going to call it the dot product. So we're going to pick two vectors in Rn, u and v, and define the dot product as the sum of the products of all pairs of components. Okay, in other words, if u is u1 up through un and v is v1 up through vn, then u dot v is u1 v1 plus u2 v2 all the way up to plus un vn. Okay, strange thing. Now, the most important thing to notice about the dot product is that, wait a second, I just defined the product of two vectors, and the output looks an awful lot like a number. It is. In fact, this is a number, a real number. Not another vector. Okay, if you were expecting the product of two vectors to be yet another vector, I'm sorry to disappoint you. Yeah, this vector is going to measure some value that depends on both u and v. Okay, but yeah, it is an honest number, and we're going to do all kinds of crazy things with it. But first, before we do anything, we should actually do an example where we take the dot product of two vectors so that you can see what it looks like. For those of you who are familiar with Excel, this is the output of the sum product function. Okay, sum product, notice it's the sum of the products of the components of the vectors, right? That's a mouthful. Try saying it yourself without putting this video on repeat. Okay. So so we have two vectors here. U is the vector 2, 3, 4, and v is the vector 1, negative 2, 0. Well, then u dot v is 2 times 1 plus 3 times negative 2 plus 4 times 0. If you multiply that out, 2 minus 6 plus 0 is negative 4. So the product, the dot product of these two vectors is the number negative 4. We will not talk about this in this video, but the dot product is a special case of something called an inner product, which is an additional piece of structure that can be given to vector spaces. Those are topics that are for the end of this course. But for now, the dot product is going to become a very, very good friend of ours. The first thing that we should talk about is a collection of properties, algebraic properties obeyed by the dot product. So we'll state this as a theorem just like we saw in the last video. Our theorems are mathematical statements about properties or behaviors of different mathematical objects. So for example, let u, v, and w be vectors in Rn, and let c be a scalar. Then, okay, first of all, the dot product is commutative. In other words, if you multiply, well, if you take the product u times v, or u dot v, that is the same as the product v dot u. Okay, and notice that's just because for each term in the sum, u1 up through un, or u1v1 all the way up to unvn. Every single one of those products is a product of two real numbers, and the real numbers have the commutative property. Um, and so, yeah, so switching the order of the product doesn't matter. The next one is a form of distributivity. If you have the product of u times the sum of v and w, then you could have done the dot product u dot v and u dot w, and then added the two resulting numbers together. Okay, we will prove that one in just a moment. Next is a form of associativity, in the sense that if you were to scale the vector u and then dot with v, you could have taken u dot v and scaled that number by the original scalar that you were using on u. You'll get the same number. Proofs for 1 and 3 are in the book, so we're not going to go over them in this video. And then the last one is looks a little bit intimidating because there's a symbol in there that we haven't seen. But it says that if you take u and do the dot product of u with itself, you will get a number which is greater than or equal to 0. And then it says moreover, so more importantly, the only time that you will get the number 0 is if the vector u itself is the 0 vector. Okay, so in other words, this, by the way, this property is called positive definiteness. That does not matter, won't be on the test, but in case you wanted to know what it's called, the idea is that when you dot a vector with itself, you'll always get a positive number, unless you dot the 0 vector with itself, in which case you'll get 0, which is technically not a positive number, right? And so, right. Oh, by the way, this symbol means if and only if. In terms of rigorous logic, this is saying that what it means is a two-way implication. So suppose you're out in the wild and you find a vector that when you dot with itself, you get the number 0. The arrow in that direction is telling you that, by the way, that was the 0 vector. Or suppose you're out in the wild and you discover just the 0 vector and you want to dot it with itself. Well, the backwards arrow is saying that the only number that you'll ever get is 0. Okay? Both are pretty obviously true just by the definition of the dot product. But what we're saying is that each one of these facts implies the other one logically, right? And that's what we're doing with our mathematics, right? We're studying logic in a very almost applied way, right? And so we're using it to prove mathematical statements. And so having a two-way logical implication is very powerful for that reason. Okay, let's prove number 2. So we start with u, and we want to dot with v plus w. V plus w is, well, all three of these, u, v, and w, are vectors in Rn. So let's write them as such. We've got u1, u2, all the way up to un. We're going to dot that vector with the vector v1 plus w1, v2 plus w2, all the way up to vn plus wn. Now, I skipped a step here. I should have written, giant parentheses, v1 up through vn plus w1 up through wn, and then done component-wise addition. That would be by the definition of vector addition. But in order to save time, space, and to sort of push you to think a little bit more abstractly about these ideas, I'm sweeping that first step under the carpet, and I'm just writing what is actually the sum of v plus w. Well, it's a vector in Rn, and its components are v1 plus w1, v2 plus w2, and so on, right? Okay, great. Now, by the definition of the dot product, which is kind of the main part of this theorem, well, the dot product says go and multiply all the pairs of components together and then put plus signs in between each of the products. Okay, we can do it. U1 times, that's the first component of U. We're multiplying by the first component of the sum, V plus W. So we're multiplying by V1 plus W1, that sum. Plus U2 times V2 plus W2, right? We're taking the first component and multiplying with the first component. Then the second component multiplied with the second component, and so on. We'll keep doing that process all the way until un vn plus wn. Yeah. Now, just like in the last video when we were doing a proof, our goal was to, we have a statement about the behavior of vectors, okay? And our goal was to port that over to a statement about real numbers. And here we have a statement about real numbers. We can rewrite this as by the distributive property of the real numbers. U1 V1 plus U1 W1 plus U2 V2 plus U2 W2, and so on, right? I just apply the distributive property to every single term in the green sum. Okay, all the way up to un vn plus un wn. Now this is a sum of, I guess, 2n real numbers. I guess more importantly, it's a finite sum of numbers. We're just adding together a bunch of numbers, which means I can rearrange the sum as I want. So what I'm going to do is I'm going to collect all the v's at the very beginning and all the w's at the very end of the sum. So we'll write this as u1 v1 plus u2 v2. That's like this guy, then there's another one, all the way up to this last one, plus dot, 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 up to un vn plus u1 w1, that's the first term that has a w component in it, and then u2 w2 all the way up to un wn. Now, why would I do such a thing? It's because, do you recognize the definition of the dot product in here? This is precisely u dot v and u dot w. We're done. We've actually finished the whole proof. It was right around the corner. By the way, this symbol is a tombstone. I think it's because they lay the problem to rest, or the proof to rest. I'm not sure, but it used to be. I almost wrote R.I.P. It used to be QED. QED. But it's a symbol that people draw nowadays in modern math to indicate that they've completed a proof. Ironically, for all the proofs given in our textbook, not a single QED or tombstone shows up, so that's disappointing. It's very satisfying. It's meant to be a very satisfying end to the proof. So you'll see me do that as we prove different things in our course. Okay, so that's enough about what is the dot product and how does it behave. Let's turn this now into a collection of geometric observations. So first of all, let's talk about the length of a vector. This is going to come straight out of the Pythagorean theorem. If you have some vector, whatever, in standard position so that its initial point is at the origin, if you were to compute the distance from the initial point to the terminal point as points in the plane, you would just drop a vertical line, make a right angle, a squared, b squared, c squared. Okay? As it turns out, that's a perfectly well-defined notion of distance in any number of dimensions. And so what we do is, before we do that, let's take a look at these components. If this vector that we've drawn is the vector AB, I'll call it V. V is the vector AB. Then notice that V dot itself, which is something that we discussed in the previous theorem, V dot with itself is defined as, well, you take the first component, okay, I'll write it out. It's AB dot AB. And then by the definition of the dot product, this is a squared plus b squared. Now, if that looks an awful lot like the square of the distance from the initial point to the terminal point, you're absolutely right. C is just the square root of a squared plus b squared. The positive square root because we, in theorem 1.2, part 4, we specifically said that the dot product of two vectors is always a positive number. And we just take its square root. The square root of a positive number will still be a positive number. Okay, and in fact, notice we could have just taken the square root of v dot v. Let me get rid of that. Instead, that will still give us a number. And we actually take whatever that number, that output is, as the definition of the length of the vector. We'll call it the length of the norm, or also you'll see the magnitude of a vector v. And it goes like, we use a double absolute value bar to denote it. And it's the norm of v is the square root of v dot v, also known as the square root of the sum of the squares of the components. Pause and rewind if you need to hear it again. Yeah, it's a mouthful, right? But we just add up we take every component, square it, add all of those squares together, and then take a square root when we're done. Okay. Let's do an example real quick. Just the square, classic 3, 4, 5 triangle. So if you want to take the norm, by the way, I will use the word norm of a vector rather than length. That's because, again, just like the dot product is a special example of an inner product, the length of a vector is a special example of a type of norm. Okay, and so I'll just call it norm, right? That's what it is. So okay, the norm of the vector 3, 4 is, well, you got a square root 3 squared plus 4 squared, which is root 25, also known as 5. So the length of the vector 3, 4 is 5, right? Now, another way of, this is just more of a side comment, which is that if you square the norm of a vector, that is precisely the same as taking the dot product of the vector with itself. That comes in handy when trying to prove things about dot products or norms or things that involve dot products and norms. And we will actually use this, at least some, in this video as well. So stay tuned, right? But it's a very handy observation, which is that the norm of v times the norm of v is v dot v. Those two are the same, right? That's just by squaring both sides of the definition. Okay. Good. So now let's look at just another theorem about the behavior of norms of vectors. So let V be a vector in Rn and let C be a scalar. Then the norm of V is precisely 0 if and only if V is the 0 vector. This is actually just that first part is just a restatement of part 4, the second part of part 4 of the previous theorem, right? It's just saying that for a vector to have a norm 0, then when you dot product it with itself, you have to get 0. But that can only happen if it's the 0 vector, right? So it's literally the same. Number 2, though, says that if you take the absolute value, if you take the norm of a scalar times that vector, what you could have done is taken the absolute value of the scalar and then multiplied it by the norm of the vector. Absolute value, we'll see in just a second. So we're actually going to prove that one. Okay? And the way that we're going to do it is we're going to look at what is the norm of CV squared, the square of this norm. Remember, CV is just a vector. It's a scaled vector, okay, but you just go and multiply all the components of V by the scalar C. When you do that, well, because it's a vector, the square of its norm by our observation is just the vector CV dot itself. Right? So by let's see, property, I'm not going to remember the number, so I'm going to scroll up and look. This is common practice, by the way. By property 3 of theorem 1.2, that's what we're going to use. Okay, by property 3, I want to take a scalar times a vector dot another vector. Well, I could have just done the scalar times the vector dot the other vector. That was theorem 1.2, part 3 applied right here. You know, you have a scalar times a vector times another, or dot another vector. Well, that's exactly our situation. We just do the dot product first, then do the scalar. And by exactly the same reasoning, we can take the scalar on the inside of the dot product and pull it to the outside. So in other words, we are looking at C squared times V dot V. Okay? But V dot V is just the norm of V squared. So this is actually C squared times the norm of V squared. We haven't really gotten anywhere except for one fact, which is that we can take the square root of both sides of the equations. Notice this is saying that the norm of CV all squared is C squared times the norm of V squared. Well, if two things squares are equal, then taking square roots tells us that each of those things themselves is equal. They're real numbers, right? The norm is a real number, and C is a real number. They're both, C is a scalar. And so taking the square root of both sides, we have the norm of CV is the square root of C squared. Let me write that for you this way. Absolute value of C, because the square root of something squared is literally its absolute value. And then we take that and multiply by the norm of V. Not squared, we took the square root, right? That's it. This is what we were trying to prove, number 2, right? So we had to do some algebra and then apply facts about the behavior of the dot product in order to finish proving this theorem, okay? Now, what happens when a vector has length precisely 1? Actually, it's kind of amazing how convenient it is to have length 1. So we give such a vector a name. A unit vector is literally just a vector with length 1, or with norm 1, right? Unit vector. What's nice, so unit vectors, by the way, are in 1-1 correspondence with points on the unit circle, right? Because, perfect circle. Because, right, any point on the unit circle, that's a point in the plane, it picks out a unique vector whose initial point is at the origin and whose terminal point is the point that you've chosen. And, of course, the length of this vector is 1. You just do Pythagorean theorem, or dot the vector with itself, right? And so, yeah, so points on the unit circle, 1-to-1 correspondence with unit vectors. What's great is we can take any other vector and normalize it. So in other words, given any vector in Rn, one moment, given any vector in Rn, technical difficulties, I guess. We can construct a unit vector which is pointing in the same exact direction as your vector. Unit vector in the same direction. Okay? By dividing each component by the norm of that vector. I'll just say by dividing through by the norm. So let's do an example real quick. Okay, let's take the vector 1, 2. That'll be fun. Let's call it v equals 1, 2. Then let's let w be v divided by the norm of v. The norm of v, I will just tell you verbally, or I'll just write it here. Yeah, we'll do like this. It's v divided by 1 squared plus 2 squared under a radical is root 5. You can also, v divided by the square root of 5 is just v times 1 over root 5. It's just v times a number, right? And so it's a scalar multiple of v. It's not a whole number, that's for sure, right? But don't let the fraction bar wig you out, okay? This is just the vector 1 over root 5, 2 over root 5. And I will leave it as an exercise for you to verify that this is a unit vector, right? You just dot with itself, and you should obtain a length of 1. You will. Okay, good. There's one last thing to talk about when it comes to unit vectors, which are the standard unit vectors. Standard unit vectors made an appearance even in the last video, and they will continue. They're, in some senses, the nicest vectors that we know. These represent a single unit in either the x or the y or z direction. We usually denote them with subscripts. So e and then 1, whatever. E1 we'll call 1, 0. E2 is 0, 1. Okay, and as vectors just in the plane, they're like 1 unit in the positive, or in the positive x and positive y directions, right? Those are the ones that mark out our axes, our standard axes. We saw in the last video, actually, that you don't need to use the standard axes to locate all the points in the plane. You just need 2 things that are not on the same line as each other, 2 vectors that are not scalar multiples of one another. Okay, these guys do the job. They do the job really, really well because they line up as vectors with our homegrown intuition about what points in the how to locate points in the plane, right? You can do this, in higher dimensions. So you're gonna have E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. And those correspond to unit vectors in the x, y, and z directions in R3, right? And so on. Okay, good. So we have one last thing to talk about when it comes to length, which is 2 theorems that get honorable mentions in the textbook and deserve a lot more attention than they have. We have, they're both statements about inequalities. So the problem is we would love to have that the absolute value of the dot product is equal to the product of the norms. Absolute value because the norm is always positive. You multiply the 2 norms together, a norm of 2 vectors, so any vector u and v. If you multiply their norms together, you'll get a positive number. Wouldn't it be nice if that number was just the output of the dot product? Maybe absolute value. The answer is no. In fact, rarely. However, if you if you replace the equal sign with a less than or equal to symbol, then you do get a true statement. It's true for any pair of vectors that if you take their dot product and then take the absolute value, that number will be smaller than the product of the norms of the individual vectors. It's called the Cauchy-Schwarz inequality, and it is pivotal in proving the next equality, which is one that you definitely have heard of. You just may not know it. It's called the triangle inequality, and it basically says, well, wouldn't it be nice if I could just say that take 2 vectors, add them together, and take the norm of the new vector? Wouldn't it be nice if that thing's length is equal to the sum of the lengths of the other 2? And again, the answer is pretty much never, unless u and v are on the same line. However, if you again replace the equal sign with an inequality, then you do get the thing that you want. This one, let me draw the picture for you, so that you'll see why it's not true that it's an equal sign. By the way, be very, very careful when doing computations involving specifically this guy, the absolute value, or the length of the sum of 2 vectors. Be very careful that you don't just, oh yeah, that's equal to the length of the sum is equal to the sum of the lengths. No, 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 no. The length of the sum is less than or equal to the sum of the lengths. Okay. Now, I claim that you know this already. So let me draw some vectors. Here's u, here's v. I'm not even labeling them apparently. Okay, we want to do their sum. We do tip to tail. Oops, tip to tail, and we draw a vector. Almost worked. Okay, so here we've got two vectors being added together, and then we're going to go and compute lengths of everything. So let's go and do this. I have to be careful not to. There we go. That was easier than I thought it would be. So we were hoping, the hope was that if I were to just add the blue arrow and the red arrow together, I would get the same length as the purple arrow. That won't work. And here's why. Just go and actually try it. Sure enough, no such luck. The red arrow sticks out past the purple arrow. But notice that, in other words, the purple arrow is shorter. The length of the sum is smaller than the sum of the lengths. Yeah? Okay, let me rephrase this in a way that you have definitely heard it before. The shortest distance between 2 points is a straight line. Shout out to the glitch mob. Okay. That wasn't, I just dated myself, I'm sorry. Okay. Well, in other words, if you have any two vectors and you take their sum, you are going to get, you do tip to tail to get to some location. You could have gotten to that location in a shorter length, like less number of miles walked or whatever, if you had gone directly from the tail of u to the tip of the sum. Okay. The one time that this holds is when the vectors are in a straight line, in which case, do you want to do one and then the other, or do both at the same time? Okay, well, that's the same path. Yeah, okay, good. I won't prove this one. There is a proof for the triangle inequality in the book. There's not a proof for the Cauchy-Schwarz inequality. Okay, that's enough about length, but we do want to mention, give a shout out to the concept of distance as well. Like, what does it mean to have the distance between two vectors? I mean, vectors are, arrows or something. So do you go, certainly it's not computing the distance between the tails. And also there's this thing about standard position where like I could just move the vectors anywhere, right? And it's still the same vector because it has the same direction and magnitude. So it's not like you can do the distance between terminal points either. But what you can do is the distance between terminal points while the vectors are in standard position. Oh, whoa. And that's exactly the notion that we're going to do. That will correspond exactly to the notion of distance that we use, distance between 2 points in the plane or something like that. Okay, so the definition of distance is that the distance between two vectors is the norm of their difference. That's true like as points on a number line. If I've got 1 and I've got 3, the distance between them is the absolute value of the difference of the numbers. If it's points in the plane, here's a 1 and a -1. Then I have to subtract all the x components and the y components and so on, and then square each of those things and then do Pythagorean theorem. In other words, I have to compute this side length, which is the difference of the x values, this side length, which is the difference of the y values, square each of those, add them together, take a square root. That's exactly the process of computing a norm. But the norm of what? Well, it's the norm that you get when you subtract x values, y values, or written as vectors, it's the norm that you get when you subtract the components of the vectors whose terminal point, vectors in standard position, whose terminal points are the points that you're trying to compute the distance between. That's all there is to it. So let's do a 3D example, which I'm not going to draw because that's a little bit beyond the scope. But let's take a look. The distance between u and v is, it's defined as the norm of course, u minus v, which is the norm in this case of 1, 1, 1 minus 2, negative 1, 5, which is the norm of 1 minus 2 is negative 1, 1 minus negative 1 is 2, and 1 minus 5 is negative 4. Okay, the norm is once again, we just square each component and then add, and then square root when we're done. So it'll be the square root of negative 1 squared plus 2 squared plus negative 4 squared, which is the square root of 1 plus 4 plus 16. It's root 21. Is what it is, right? That's all there is to it for computing distance. Pretty straightforward. That was a terrible pun, and I'm sorry. Okay, angles. So the last topic that we wanted to talk about are, well, if you can compute the distance between two vectors, can you compute the angle between two vectors? Notice I've written in parentheses here. So what we'll do is we will label the angle theta, and we're going to assume that theta is between 0 and pi, so 0 and 180 degrees. Because, like, what if I have this situation? Here are my two vectors. Do I want to take the smaller or the bigger angle? There's not much difference between them, but I want to take the bigger or the smaller angle. Okay, just so that we have a sensible notion of what angle means, right? So this one, we're going to arrive at the definition of the angle between two vectors, but we're gonna have to we're gonna develop the idea behind it. So what we'll do is we'll appeal to the law of cosines, which is, in my opinion, one of the highlights of a trigonometry course. I'll state it in terms of vectors, but I won't go into the details of the geometry behind it. It basically says that the norm of one of the sides, u minus v squared. By the way, the law of cosines is a generalization of the Pythagorean theorem for triangles that are not necessarily right triangles. Okay. So it says, okay, you want the square of a third side. It'll be the first side squared plus the second side squared. So that's the length of u. So if we're looking at the third side being the difference u minus v, then the first two sides are u and v themselves. And then the last side is going to be this u minus v thing. So we want to compute the square of the length of that third side. You start by adding the squares of the lengths of the other two sides, Pythagorean theorem style. Then you subtract, when you do this, you'll overcount by some amount. The thing that you overcount by is 2 times the length of the first side times the length of the second side. Oh, I can't put a dot there. This is going to be confusing. Times the cosine of the angle between them, which I need to somehow squeeze in here. we'll just make sure that there's enough space. Here we go, cosine theta. This is the law of cosines, stated for vectors, okay? It's a theorem from geometry. We start here, and then we're going to apply that fact that the square of the norm is the product of a vector with itself. And we're going to use that fact a lot. Okay. So, first of all, when applied to the first difference, or the first side, I guess, this is looking like u minus v dot u minus v. On the right-hand side, I'm just going to copy that. Give ourselves enough space to work here. Using a lot of properties of the dot product. So remember, the dot product is distributive. I guess that's the only property that we're using. Distributive property several times. This left-hand side, u minus v dot u minus v is, okay, u minus v dot u minus u minus v dot v, right? You just, I'm viewing this entire first u minus v as it's just a vector, right? And so what I do is I multiply that by each other vector in the sum, distributive property style. Then I can go and distribute this u to each of the two, and this v to each of the two. And so what we're left with on the left-hand side is u dot u minus 2 u dot v u dot v plus v dot v. Okay, just by applying the distributive property a lot, or FOIL, honestly. Okay, good. And I'm going to clear our scratch work so we have enough space. And so now what we're left with is, this is of course equal to the right-hand side. What's left is, remember, u dot u is exactly the norm of u squared. That's the property that we used to start this whole left-hand side procedure, which means that I have the same object on the left and right, the same value being added. I just subtract it from both sides. It just has two different names on each side of the equation. Look at that. I can pull that trick twice because v dot v is the same as the norm of v squared. And what's left on the left-hand side is negative 2 times u dot v. And what's left on the right-hand side is negative 2 times the norm of u times the norm of v. Well, I can divide both sides by negative 2. And what I'm left with is apparently the fact that u dot v, for any two vectors, u dot v is any two non-zero vectors. Yeah, any two non-zero vectors. U dot v is the norm of u times the norm of v times cosine theta, where theta is the angle between them. So apparently there is a formula for precisely the angle between them. We're going to state it with the cosine just by dividing both sides by the number being multiplied by cosine here in this equation. But notice you just take arc cosine of both sides in order to find what the angle itself is. But to find the cosine of that angle, it's a purely algebraic procedure. You just dot the vector with, or dot the two vectors together, take the two norms, and then divide one by the other. In other words, cosine theta, so definition. This is the definition, I guess, of the angle between two vectors. And it goes like this. Cosine theta equals u dot v divided by the norm of u times the norm of v. I just divided both sides in that last equation by norm of u times norm of v. Okay, this is surprisingly helpful when doing computations. Just anytime you want to find the angle between two vectors. Okay, and we'll just finish up with an example. So if we take u to be, finish up. There's one more concept we need to mention after this. Okay, it's important. Okay, so we're going to take u and v, and we're going to find the angle. Apparently, we're going to show that the angle between them is roughly 71 degrees. Okay, the goal is, so the procedure is cosine theta is, I'm just going to write the formula for it, u dot v over norm u, norm v. Okay, we should just compute those three. There's three numbers showing up. Apparently it's the ratio of three numbers. And so we're gonna just compute each of those numbers separately. So u dot v is the easy one. Just dot product these vectors like we did in example 1 or whatever. That's multiply each component together and add when we're done. I will do that verbally. This is 1 times 0, which is 0, plus 3 times 2, which is 6, plus 3 times negative 1, which is negative 3. So u dot v equals 3. The norm of u is u dot with itself and then take a square root. Well, u dot with itself is 1 times 1 plus 3 times 3 plus 3 times 3, all square root. I'm getting square root of 19. We'll write one step in there. Square root of 1 plus 9 plus 9 equals root 19. Right? U dot u, take the square root. And then finally, the norm of v is, well, v dot v, square root. So square root of 0 plus 4 plus 1, so root 5. So cosine theta is 3 over the square root of 19 times the square root of 5, also known as 3 over root 85. That's a bad number. But if you do arc cosine of 3 on root 85, you get roughly 71 degrees. That's that. Okay, so the last concept is a natural consequence of this definition of angle between two vectors and cosine. So notice that if the angle between two, so we'll just go backwards. If you knew that the angle between two vectors was pi over 2, 90 degrees, a perfect right angle, and if you knew that the vectors were non-zero, then, well, by the formula, u dot v over norm of u, norm of v, the only part of that can make the actual output 0 is the numerator u dot v. In other words, u dot v has to be equal to 0 when two vectors are at right angles to one another. And you might ask, what does the dot product have to do with uh, this notion of right angleness? Um, in fact, it's so significant that we give it a definition, and it's like a fancy name and everything. So we said, and so I'll tell you what that definition is. Two vectors u and v in Rn are orthogonal to one another if their dot product is zero. By the way, I didn't say non-zero vectors in the definition. It turns out the zero vector is orthogonal to every vector in Rn. I challenge you to try to take the dot product of the zero vector with any other vector. Tell me what you're going to get. Yeah? Put it in the comments or something. I don't know. Okay. Right. But okay, let's do a not silly example. 1, 2, 3, and 1, 1, negative 1. Well, 1 times 1 plus 2 times 1 plus 3 times negative 1 is 3 minus 3, which is 0. So these two not random, these two vectors in R3, they're like, if you want to try and draw them, 1 will be like go over 1, go over 1, go up 1 somehow. Yikes. It'll be like here, I guess. And then the other one, 1, 2, 3, go over 1, go over 2, and then go up 3. It'll be like up here. And there's like a right angle between them. It's like sticking out of the plane of this two-dimensional screen. I don't know. Okay, but they are at right angles to one another. In other words, or more precisely, they are orthogonal to one another. Okay, so that will be all for this video. Next time, we'll pick up with section 2.1. I'll just say a brief word about it. There's more to linear algebra than just vectors. Vectors are the main object that we're going to use. But starting in section 2.1, we'll kick it off with studying systems of linear equations. I will see you in that video.